Mm, okay, it's live.
Okay, great. Well, good evening, everyone. Welcome to a special Google Hangout session for the Y Prize to answer questions that you might have about the competition. So my name is Vijay Kumar. I'm one of the faculty founders of this prize, and on behalf of the School of Engineering and Applied Science and the Mac Institute, I want to welcome you. I think it would be good if we just go around the virtual table and introduce ourselves. So I am in my home in Wilmington, Delaware, but we have tech consultants at Penn, so I'll ask them to introduce themselves, starting with Helen.
Hi, I'm Helen. I work in Professor Turner's lab, and I'm working on tunable adhesion specifically, so if you have questions on that, I'd be happy to answer them.
Hi, my name is JK. I'm in charge for the fast charge batteries. I'm also happy to answer your questions if you have any.
Okay, so this is a Q&A session, so I'm going to assume that some of you have questions, and that's why you've dialed in. So if you don't have questions, we won't say anything.
Great.
So
There's
Vijay,
zero spectators.
they've gone? Oh,
Spectators.
Vijay, you might want to invite them to type their questions.
So
We have the Q&A app.
I see. So I am trying to see where the Q&A is, or do you? Oh, okay, there we go. So there's a Q&A button on the left side of it. You should have a Q&A button on the left side of your screen, and you can submit your questions, and we'll try to answer them as to the best of our abilities.
Maybe if we have no questions in the meantime, Vijay, you can talk a little bit about what constitutes a good submission in case any of these participants did not attend the Create Your Proposal event.
I can do that, but let's pause and see first if there are any questions. Maybe not. Okay. So I assume everybody who's listening in knows the key premise of the Y Prize. It is an opportunity for you to think about ways in which you can commercialize intellectual property that's been developed at Penn in the broad area of nanotechnology, and specifically in the labs of Charlie Johnson, Kevin Turner, and Mark Allen. So Penn Technology and IP refers to a couple of different things. So if you were at the kickoff event and if you visited the web page, you will see there are three broad technology areas, each area being linked to one of the three laboratories that I just mentioned. So you might think about how to take the disclosures from those laboratories and think about ways of bringing those ideas to market. So that's number one. Number two, you can also think a little more broadly and ask, so what is the know-how that's contained in those labs? In other words, if you talk to the tech consultants, if you look at the web pages of the labs, if you look at position papers written by the investigators, you will come to know of technical expertise that's quite unique to those laboratories. And that might be able to file patents and build an intellectual property portfolio on top of IP that has already been invented. So specifically, for example, we had a question during one of the last sessions which had to do with what IP exists around graphene, and if that IP also includes the IP surrounding carbon nanotubes. So even though the particular technology that's being discussed centers around graphene, Charlie Johnson's lab is also a world-renowned leader in carbon tube technology. So you might think of ways that you might be able to leverage technology that's been developed in his laboratory, as well as know-how that is limited to members of his group. So that has not been protected as Penn IP, neither has been disclosed as such, but the minute you think of new ideas that actually build on the know-how in his laboratory, that immediately becomes new IP. And so you might think about taking the lab's work in directions in which investigators and the students have not taken them. So that's another way of expanding on the idea of a Y prize.
We have 5 people online. Does anybody have any questions?
Do you guys at the other end, the tech consultants, do you have anything that you would like to add? Have you been asked questions that perhaps you'd like to share the answers to a broader audience? No?
No.
Maybe I can share something.
Sure.
Many group ask me many different questions, but there are some technical questions and non-technical questions. But it is good to know that I received many questions. So one of the very tough question was, by the way, I'm in the fast charge battery part. Since there is a commercial available batteries, our technique is it may not be value for the commercialization term. And that was exactly what some of students asked, students' comments. And I think there are Toyota Camry and Honda Civics. So those are good commercial cars, but so we have a different technique with the valuable stuff. And many other students also ask me, compared to the iPhone battery, how's the performance of ours? And that's exactly in the slide, but our battery is lighter than the iPhone battery, and with even a given same volume, we can store more energy, and we can charge faster and discharge faster as well. So that was the most common questions to me. At least 6 or 7 questions were given as the same type of questions.
Can I ask a question about that some teams might be thinking about? Because you're saying that it's already commercially available, fast charging batteries. But one of the things that I think Mr. Fitzsimmons had mentioned was using the same technology that's available and doing something else and finding a new use for it, as opposed to doing the same things. Is that something that teams could be considering?
I'm sorry, I lost your connection there for a little bit. Could you repeat that again?
No, one of the things that JK's one of the questions that he had was that the fast charging batteries, that technology has been commercialized, or some aspects of it has already been commercialized, or have already been commercialized. And I believe one of Mr. Fitzsimmons' comments on using the technologies was not just using it as it had been envisaged by the researchers, but taking the same technology, even if it had been commercialized already, and using it for something else. And
yeah.
Different purpose that was.
Right. So I think oftentimes the basic technology, which you would refer to as a horizontal, right? So that's what we do. We push out ideas, and that create the intellectual property platform. But oftentimes it's the vertical, the applications that add that add value to the basic intellectual ideas. So you might think about, so just to take an example, you might think about a battery that's been commercialized for vehicle applications, which have a certain type of specificity to them in terms of the charging rate, the discharge rate, the specific power, the specific energy, and so on and so forth. But the very same device, if you use it for a different type of vehicle, so for example, I happen to work on flying vehicles, the needs are very different. Or if you want to use it for personal computers or for wearable devices, the needs are very different. And so the same idea can add value in unique ways. And part of how meritorious your idea is really depends on what new applications you come up with. So that certainly yeah. So are there any other sort of questions, technology-related questions you guys have received besides the one on batteries?
Yeah, I keep getting asked about how strong is the adhesive, and we only have like a low ball estimate on that. And we think a square that's about 2 inches by 2 inches can support around 440 newtons of load. So that's something that people keep asking, but we think it could get better than that.
So can you project? Do people have the material to allow them to speculate, to project forward?
Can people have like physical objects?
No, is there evidence that allows?
Yeah. So currently, all of our measurements are on single posts, but we think by having an array of posts, we get better adhesion. And part of that's this phenomenon of contact splitting, but we haven't actually tested it ourselves to see if it'll work in this case.
Very good. So have you guys envisioned uses for these kinds of materials, the tunable adhesives?
Oh yeah, that's our goal. We're planning to scale it up.
What is your best idea? Since nobody else is coming up with questions, let me ask you a question.
Okay.
So what is your best idea thus far?
Sorry, we didn't hear you.
I said, what is your best idea on how to use this technology?
Oh, and how to use it. So for us, we're like mostly focused on MEMS devices and building MEMS devices and transferring components of MEMS devices to make things that wouldn't be possible in a traditional clean room, just based on the types of sort of the techniques that are available. It's hard to combine sort of two very different things. But with transfer printing, you could lift up this component and put it over here and interface it with that component, which you normally wouldn't be able to make. And so that's sort of our idea behind it. We also like the idea of attaching it onto robots and having them climb, but we have really no expertise with that.
Very good. So what are some cool applications for using graphene?
Well, graphene has the main drawback that you can't really turn it off. So most transistors in electronics have an on state and an off state, and that's why we can use them as switch. So any real application that you have has to consider the fact that you cannot turn graphene off. So people tend to use it, the most common uses tend to be as using graphene not as a semiconductor but as a metallic contact. So the biggest application that I've seen has been a big push to replace indium tin oxide as a conductor for solar cells in their fabrication. Right now it's a more expensive material, but certainly with enough scale it could be cheaper than ITO.
There's a lot made of using graphene for solar arrays.
Yeah. So the good thing is you can scale it up at the moment with current technologies. You can scale it up to make really big arrays for them. So you don't make the entire array out of graphene. You make the array out of normal materials, and the top conductor, which has to be transparent, is the one that is made out of graphene. The main advantage of this is that it's mostly transparent. It's 98% transparent, and it conducts electricity better than any other material, much better than ITO certainly. There are much lower losses, so in terms of how much energy of that solar, of the sun that you capture, you transfer to electricity, the efficiency can be much, much higher with that.
So here's a application of, I'm just let me check to make sure we have no question. Oh, there is a question here. So the question that's being asked by Winnie Cheng is, how much does a 2x2 inch of the tunable adhesion material cost?
Okay, so I've gotten a few questions on cost, and I'm not an economics person or a business person, and I think the cost of creating this in the lab and the cost of creating it in industry are going to be very different. And so for me to create a 2-inch by 2-inch tunable adhesive, it costs a lot because I have to go into a clean room and I have to sort of do this in a serial way where I make one square at a time. And I think that if you're running an industry based off of this 2-inch by 2-inch square of tunable adhesive, you would probably have your own process to do this where you make much larger sheets and you cut them down, or you make hundreds of 2-inch by 2-inch squares. And my best advice on how to figure out the cost of this would be to look into injection molding, because I think a lot of the costs would be the same, where you'd need sort of a mold to make the outside of it, and then you would need to buy the elastomer, the outside of it, and you need to buy insets. But I think both of those would be pretty minimal compared to the sort of startup of building an initial mold.
So, Winnie, if I translate that, I would look at all the array of products I can buy for very little cost that are injection molded. Pretty much anything made out of plastic, injection molded. And then it's the raw materials, the cost of the elastomer, and things of that nature. And again, to scale, these things can be brought down significantly. So that is the pitch I would take if I was going to try to create a product out of this. I hope that helped, and if there's a follow-up question, please do ask. So going back to graphenes and perhaps talking about using graphenes in the same space as batteries, one of the big stories that came out, I remember not too long ago, was about high-power graphene supercapacitors. So if you did have high-power, inexpensive, high-specific power graphene supercapacitors, then we don't need fast-charging batteries, do we?
Well, I would say it's different because the rate of charge doesn't necessarily mean how much charge it can store, which I think is the main advantage that graphene offers. I think the biggest advantage here is sort of a surface area increase. And I'm not exactly well versed on how these batteries might work, but I would imagine they either use it as a coating in the electrodes to increase the amount of charge that they can charge. They do the same thing with silver nanoparticles in some batteries and things like that. Maybe
Right. Once the capacitors start to store longer, we no longer call that as a capacitor, but rather call it as a battery. So it is kind of very similar technology. And as you mentioned about the surface area, we used to see both capacitors and battery trying to increase the large number. A larger surface area to hold the more ion transportations and higher voltage in between. But for storage point of view, we need more on the chemistry than the electrical aspect. And capacitors are more on the potential differences, and it quickly discharges and cannot store that long. So there are kind of differences. But also somehow it is true that Professor Kuma mentioned that there will be kind of vague area in between battery and supercapacitors, because these days supercapacitor can act similar like a batteries, but battery stores longer. But supercaps are challenging to battery, like so. Somehow there's a gray regions that I agree.
Very good. So for those of you who are online and who might have tuned in late, there's a Q&A bar on the left side. There should be a Q&A bar on the left side of the screen, Q&A button that you can use to ask questions. So we have another question, and this one from Matt Chan, also about tunable adhesion. Are you able to see these questions?
Yeah, we can see them.
Okay, but let me just read them out for those of you who cannot see them. So the question is, the tunable adhesion slides show that this technology can be used for building robots that climb up walls. How is this possible when the technology doesn't stick when applying shear force?
Yeah, so I think you have to think about it in a slightly more creative way, where if you just have a wall here and you are applying a force like this, it's naturally going to pull down. But you might have to have it apply a force this way so that when it pulls down, it's actually more like a normal force. We don't use these as robots for climbing walls, so we haven't thought that out exactly. However, I think there's the potential for it to work. Maybe it would be better if we had him climbing across the ceiling as opposed to a wall. But I think you probably could design a robot such that when the force accounts for the weight, it is more like a normal than a shear. It's a good question.
So how does this, just following up on that, how does it compare to how gecko feet actually how gecko feet actually do function? In other words, how do gecko actually hold on to walls?
So our adhesive is completely axisymmetric. So
Just about a second.
yeah, so we have this inset in the center, and we have a material around the outside, and the inset's right in the middle. Which for us is really nice because we can apply a shear load in any direction and have the same reaction. However, geckos are very asymmetric and have a real directionality to them. So if you imagine my hand here as a gecko foot, and each of my fingers branches into more and more setae, or like more and more sort of smaller and smaller parts. If they're in this position and their arm is sort of at this 30-degree angle, if you pull this way, it has very strong adhesion and shear. And if you flip it over, it's almost like undoing a switch, and it has very weak adhesion and shear in the other direction. So you can imagine also applying the same technology by putting the inset in one section of the post. We're not currently doing that, but I think you would lose some adhesion under normal loading, but you probably gain adhesion under shear loading in the other direction.
I would imagine that if instead of using cylindrical posts, you would use square posts.
Yeah.
You would get a shear on one direction and not on the other. Design them in such a way.
Right. I think you could design it to do that.
And
if
then
you
that
have
way,
that,
when you're pulling down, you still have the shear, and to move it
Right.
out, you'd have to sort of move your
shear the
arm
opposite direction. Right.
side.
So with square posts, you do see the same phenomenon if the post is right in the center. But you can imagine moving it to the side. And
Well, I hope that answered your question, Matt. If there's anyone else that would like to ask questions, once again, you should be able to type in your questions in the Q&A using the Q&A menu selection. Looks like based on the questions, the tunable adhesion technology is the most popular one.
we're the most confusing.
With a very limited sample size. Are there other questions? you guys want to add to the discussion?
Well, we could say to anybody who's listening and might be a little, still formulating their questions, that if you go to the Y-Price website, there is a Q&A, an FAQ page, and they can submit questions to the consultants that way. And they can also email us, and we will put them in touch with tech consultants. But we do encourage you to use this resource because it is available to you and to your team in helping you formulate your idea and get your submission in on time.
Right. So are there interesting questions on the Y-Price website that were asked recently, Karen, that we could perhaps talk about?
They did have some questions on there, but I have to confess that I'm a little bit nervous about navigating away from the Hangout.
Okay, no, I, on the other hand, have no such qualms. I am all over the place, and it probably means I'm going to lose my place here, but so I am looking.
I think the questions that I remember seeing there related more to the mechanics of submission and you're creating your proposal than to the technical aspect.
Right. Well, but as Karen said, again, a good place to go to is yprice.upenn.edu, and you can ask two types of questions. One concerns, of course, the general competition, and the other is also technology-specific questions. And those questions will be answered either by the staff or by the tech consultants. Yeah.
I think the questions that I got from, through emails is more team confidential, and I think that applies in here. People doesn't want to post their specific questions so that they don't want to share their secrets to some
wider audience. Yeah.
But I got questions every day, at least more than 5 questions. So Professor Kumar, you don't need to discourage by showing that there's no question in this session. So
okay, good. Well, I'm glad they're asking you lots of questions. Are there any interesting questions that you'd like to discuss here for the benefit of those who did not ask you those questions without divulging any secrets?
I think rather than share the idea, since I'm the trustee from the questionnaire, but I think it is open house to meet each other, and I don't mind to share my time with you guys, because some questions are really, in technical point of view, not logical. So they asking like how much time it takes and after charging, how big the battery gonna be, and the volumes and chargings are not related actually. The similar questions are really being asked a lot. So maybe sometimes just email me directly is good. Also, you can just visit me. It's also good.
We have another question online, Vijay. Professor.
I just saw that, and it's also about the tunable adhesion idea, again from Winnie Cheng. How long does the stickiness last for the tunable adhesion material? Does it last forever?
So theoretically, it lasts forever. If you're doing this in a clean room and there are 0 dust particles and no dirt, it should last forever. In reality, it will decrease over time. We run tests on a pretty clean surface, but not in a clean room, and we don't see a noticeable decrease. We don't run thousands of tests. We run 10 to 100 tests, and it seems fine. But we haven't done a study on sort of degradation over time. If you're trying to pick up like dirt, then it'll only last one round. If you're trying to pick up something that's very clean, you could do it for a long time. And you can also clean it. So even if it gets dirty, you can clean it and start again, sort of.
But Winnie, one of the, if you do decide to pursue this particular idea, one of the things you might think of proposing as part of your plan is to test the material for scalability, for operation in different types of environments. And that would be a part of your plan to actually see how far you could push this idea. And you might have contingency plans if you found out that this only worked in relatively clean environments. So it is perfectly okay to go into a project like this without being certain of what the outcome is. Again, remember that a lot of these things are tested in labs by PhD students, and a PhD student doesn't get his or her thesis by just taking the material they've developed and testing it in different types of environments. So usually this kind of testing is done by companies. Did I get that right, Helen?
Yes.
Right.
We exclusively test on glass and silicon, both of which are very clean and like very characterized materials.
Are there other questions? And again, if you're tuning in late, you want to ask questions by selecting the Q&A button. On my browser, it's on the left side, and you can type in your questions. So there are no questions. Karen, we advertise this Hangout for what, half hour, 1 hour?
Half an hour.
So we're past the half an hour point. So
So I think I think we can invite people to submit questions online or to consult the tech consultants, with their team members, and thank them for joining us.
Well, before we conclude, let me ask you guys at the other end if you have anything to add. Here's a question. Is this a question? Yes, it is. So, would we be able to modify the technology so that the shear, in fact, is not symmetric? And this is again from Matt Chen.
I think you could do that. I think it would be totally acceptable. I don't have a lot of knowledge on how that would work or like research on it, but I think within the scope of this, it should be a totally fine idea. I'd be happy to chat more with you if you were interested sort of in looking at that.
Very good. Thank you, Matt, for that question. So, Pedro, you've said the least. Do you want to add anything to this discussion?
Just that it's perfectly fine. You can contact me through the Y-Prize website or directly to my email, which I've put on the slides that I provided. Any questions on graphene or scalability of graphene or different applications that have been seen on the market, I'll be happy to answer.
Well, thank you very much. Thanks for the people who joined the Y-Prize, and a special thanks for the consultants. And to Karen for organizing everything. Thanks, Karen.
You're welcome.
And sorry?
No, I was just about to say thank you.
Oh, I'm at home. I'm sitting comfortably wearing my sweatshirt, so I have no problem. So thank you, guys.
Okay, thank you.
Thank you.
Take care.